When you receive a byte of serial data, what you actually receive is a block of binary bits that is a series of ones or zeros that could be interpreted a number of ways. If it's supposed to be a positive integer, then converting it's really not that difficult. If it's a signed integer that may be negative, or if it's another data type, there's a little bit more to it. In this episode of Practical Robotics, we're going to learn how to convert binary data into positive integers, negative integers, and some other data types that you may need. I'm Lloyd, author of Practical Robotics in C++. Let's get to it.
My goal for the readers is for them to come away with all the foundational knowledge they need in electronics, hardware, robot operating system, and robot control strategy and theory, that they're able to build a complete autonomous robot.
Hopefully you're familiar with the basics of converting binary numbers into a decimal, but let's quickly review how it works. In the base 10 decimal system that we grew up with, each place in a number can hold a value of 0 to 9. Starting on the right, we have the ones place. Then moving towards the left, we have the tens place, the hundreds place, and so on, with each place increasing in value by a multiple of 10. We naturally just read the number because we grew up with it. But if we broke it down digit by digit, what we are doing is multiplying the value in each digit by the value for its place, then adding it all up for a total. The binary system isn't too different. We still start on the right with a ones place, but instead of incrementing by times 10 for each digit, the value for each place to the left doubles, or is multiplied by 2. Since we only have ones or zeros for values, it's simply a matter of whether we include the value for that place or not when we add up the total. This means a single byte with 8 bits can give us any value from 0 to 255. And that forms the basis of serial communication for both positive integers and characters like letters, and special characters via the ASCII code, where every character is assigned a decimal number to represent it. The ASCII code even has characters for each numeral, but that's a different story than what we're going to do today. So positive integers and characters are easy enough, but sending and receiving negative numbers is a bit trickier because we don't have the benefit of just putting a minus sign before the value. The secret is to use something called 2's complement. In 2's complement, the most significant bit, or MSB, is used like a minus sign instead of its normal value. If the MSB is a 0, then the rest of the bits are to be interpreted as a regular positive value. But if the MSB is a 1, then the rest of the bits are to be interpreted as a negative value by inverting each digit, adding them up, adding an extra 1, and then finally applying our minus sign. Taking up a bit for the sign indicator means the maximum positive value we can have is 127. But since we can also represent negative numbers down to minus 128, we still have 256 possible values per byte. But for this to work, you have to know ahead of time what type of data to expect, because some sensors will send unsigned values that are always intended to be interpreted as positive, and some will send signed values that might be positive or negative. So you have to check your device documentation and get your data types correct. Okay, so that's how we do positive and negative numbers under the hood. But fortunately, we don't usually have to do these conversions ourselves. In C++, we can simply tell our program which way to interpret a given byte, and the rest is taken care of for us. For example, 01111010 could be the number 122, or it could be the character for the lowercase z. And all we have to do is tell our program what we need it to be with the casting operators like these. Oh, notice that the most significant bit is 0. So even though we can tell our program to treat it as either an unsigned or a signed value, this byte will never be negative. If we look at a binary value of 10000000, now it can be either positive 128 if the device or sender intends for you to receive an unsigned value, or a minus 128 if the device is sending signed data in 2's complement. Remember when I said that you have to know what type of data the sender intends for you to receive? Well, the software libraries that you use to read serial data have likely already been written by someone else, and that programmer couldn't possibly know what type of data you are going to use his or her software for. So not only is it important to know what type of data is being sent, but you need to know what kind of data your serial library of choice is going to interpret that data as. Some libraries will provide you with an integer, and others will provide you with a character. If I'm using a Raspberry Pi, I'm a big fan of the library PyGPIO, which I will link to in the description. To receive serial data more than 1 byte at a time, I have to accept that PyGPIO is going to deliver it to me as a character, no matter what the sending device intended. It's my job to cast it to a signed or unsigned integer, or even break it down into individual bits if necessary. If the sending device's datasheet says that it is sending 2 or more bytes per value, which it would need to do if the values might be more than 1 byte can hold, then I have to combine the bytes and line up all the bits in the correct order before I can cast it from one data type to another. To keep this tutorial simple, I'll stick with 1 byte values. But in the video link here, I talk about making sense of datasheets. And in the video link here, I go into some detail about combining multiple bytes into a single value. If the data type provided by your library's function call isn't what you needed, you'll have to cast it. In C++, sometimes this happens automatically, or implicitly, when we assign one data type to a variable that is another data type. Other times, we need to explicitly cast, which means we don't let the compiler make any assumptions, and we give it explicit instructions as to what we want to happen. We can usually do this back and forth from char to int with the simple casting operators in parentheses. Although something to note is that integers can be 4 bytes long, but a char is only 1 byte. So if you assign an integer larger than 255 to a char variable, only the least significant 8 bits will be assigned and everything else will be ignored. We can often do the same to cast a char or an int to an unsigned integer, but one warning, and that is that for single-bit unsigned integers, the C++ output stream will try to display them as characters by default. A lot of values from 0 to 255 are not printable ASCII characters, and this can leave you a bit confused or thinking that you did something wrong. Placing a plus symbol in front of the variable will get cout to print the numerical value. Finally, for any of these data types, it can be handy to see the individual bits, and you can do that with Bitset. Bitset is a C++ class that basically gives you access to the individual bits in whatever you construct the object with. There's a handful of handy operations that Bitset allows, and it's worth looking them up, but for now, I just want to show you the overloaded stream insertion operator. If we do a cout statement and create a bitstream object with the variable instead of just putting the variable name, the individual bits are displayed instead of the character or decimal value. Creating your Bitset object just requires you to either be using namespace std or prefix Bitset with std, and don't forget to include Bitset. Then we have to tell it how many bits we want it to hold in the tags. And finally, pass the variable or literal that we want to see the bits of. And just like that, it's a lot easier than converting by hand if you need to check anything at the bit level. I think that's it for this video. Please let me know in the comments what you think about this video or what you'd like to see in future videos. I would appreciate a thumbs up, and we'd both benefit from you clicking that subscribe button. With my book, Practical Robotics in C++ Complete, I can finally get to a lot of video tutorials that I promise are just going to get more and more exciting. The book is off at the publisher getting formatted and ready for print, and as soon as it's available, I'll make sure there's instructions and a link in the description for where you can find it. You can also follow the Practical Robotics Facebook page for extra tips, robotics news, and of course the announcement when the book is available. Thank you so much for watching and subscribing. I'm Lloyd Brombach, author of Practical Robotics in C++, and we'll see you next time.